Hi guys, welcome to another one of RT lectures, and today we'll be looking at module 3 in unit 2. Now in module 3 in unit 2, one of the first topics that we'll be looking at is the photoelectric effect. Now one of the fundamental things of this is that it gives evidence for the particulate nature of light, and it uses the phenomenon and the works of Max Planck as well as Einstein. Now Newton as well supported that light was particulate in nature, and the results of this experiment give evidence for that. Okay, so the fundamentals of the topic are: you have a metal surface, and this metal surface obviously has free electrons, right? Now, if you have electromagnetic radiation incident on it, what you are determining is that these electromagnetic radiation consists of photons. Photons are like little packets of energy, and the energy of one photon is equal to E is equal to hf, and H represents Planck's constant, right? And that is given as 6.63 by 10 to the minus 34 joules per second. Now here you will find that once you have a packet of energy incident on the metal surface absorbs that energy and it uses it to release an electron. So what you'll find now is that from this, an electron is released. So if you have a greater number of photons, you can have a number of emitted electrons. Now, we can look at intensity, right, as being dependent on the power per unit area. So if you have a greater intensity of light, you would tend to have more photons. That is a number of photons. But we do not have any link between the number and the energy, right? Because you are considering just the number of photons present, and therefore that will increase the number of electrons. So if you have an increase in the intensity of light, you would have a larger number of emitted photoelectrons, right? But that has nothing to do with the energy. The energy is dependent on E is equal to hf. So if the incident light has to emit electrons, it has to have an energy greater than something called, or frequency rather, greater than something called the threshold frequency. Now the threshold frequency is a minimum frequency of which you have a minimum energy. Now, if you consider the surface itself, in order for the electrons to be emitted, they must absorb a certain amount of energy that is used to overcome their forces that hold it within the atom. And that energy is called the work function, right? So, initially, you would have when E is hf, right, is incident, some of that energy goes into overcoming the forces holding the electrons in or on the surface of the atom. So when that happens, right, that is called the work function, and it is given by phi. Phi is equal to hf 0. Now once you have that energy being released, right, those electrons being released, you would still have the remainder of energy it absorbs being given off as kinetic energy. So this concept can be translated down to the Einstein's photoelectric equation, where hf, the energy of your photon, is equal to phi, your work function, plus a half mv squared. So then the energy of the photon does two things. It does work to remove the electron from the surface of the atom, and the remainder of energy that the electron is released with is referred to as kinetic energy. Now, I could manipulate this equation, right? And one of the more popular graphs that are plotted, let's say I have an energy versus frequency, right? The intercept here becomes f0, and the y-intercept is phi. And the gradient of this graph is equal to h. And all of that is deduced from this equation here, right? So if I'm plotting a graph of energy is hf0 plus a half mv squared, right? Then here, right, you can look at this as the energy in joules, you could look at this as phi, and you could look at this as the kinetic energy. Now, if I wanted to plot this graph here, I'm going to now express E in terms of HF. So HF minus HF0 is the kinetic energy, a half mv squared. So this is the energy I'm plotting on my y-axis, and my frequency goes on my x-axis. So now I have successfully shown this equation into the form y is mx plus c, and c will be the work function phi, which is hf0. The gradient of the graph is equal to Planck's constant. Another thing that is associated with this is something called the stopping potential. In a typical photocell, right, you would have this scenario occurring where you would have a collector anode and you would have a cathode. What happens is when the electromagnetic radiation becomes incident on the cathode, it causes electrons to be released. Those electrons are then accelerated towards the anode, right? So traditionally, you would expect that your cathode is negative and your anode is positive, more collector plate. Now here, imagine now I apply a certain potential difference. So let's say I have a negative value here, a positive value here, positive potential, and a negative one here. So what is going to happen here? If it is that I apply a positive potential difference to the cathode, here, this is my anode, when I have electromagnetic radiation incident, these electrons, which would have previously been emitted, are now attracted back to the cathode plate. So what happens is that there is a minimal amount of electrons which are now ejected from the cathode and are accelerated towards the collecting plate of the anode. So what happens is that when that radiation is incident here, you will find that the electrons would have been ejected and it would have been accelerated to the anode. But if you apply a positive potential to the cathode, it is keeping the electrons attracted there. So you will have a minimal amount of current that is flowing. And the value of the potential difference, which just stops the photocurrent from flowing, is called the stopping potential, right? And it is really like a reverse potential difference applied to electrodes to basically work against the emission of electrons, right? And we consider now that the energy, right, is a half mv squared. But that energy is also needed, right, to cross the gap between the cathode and the anode. And we use a C-sec equation, E is equal to QV. So if I equate those two, I have a half mv squared, talking about electrons, so it's EVS, right? So now I go back to Einstein's photoelectric equation, and I have phi plus EVS. Now, if I want to plot a graph of V versus F, let's make V the subject. So it's HF minus phi over E is equal to V, right? So your stopping potential here, Vs. So then my graph of stopping potential versus frequency would be a graph like this. So the intercept of it is F0, and the slope of the graph is H over E. All right. Now these are just some, this is like the crux of what you need to know. The last thing that you would need to know when it comes to the photoelectric effect is the inability of the wave theory to explain the photoelectric effect. Because remember, at the beginning, you would have learned that light has a dual nature. So it could either be made up of particles or it could be considered a wave. Now, this experiment has given evidence that light was made up of particles. But consequently, we could consider it now to be, we could consider that the classical wave theory could not explain certain things occurring on the photoelectric effect. So the first of it is that why is there a threshold frequency? Because if you have electromagnetic radiation incident, then it cannot exceed a certain threshold value in order for emission to occur. The second thing is, as soon as the electromagnetic radiation is incident on the surface, you have the emission of electrons. But according to the classical wave theory, there would be some time delay before those electrons can absorb the energy from the photons before emission occurs. And also, it does not show any relation between the energy of your photoelectrons and the intensity. So like before, the intensity is only related to the number of photoelectrons. So if you have a greater intensity, you just have more photons, which will now, when they hit the metal surface, cause a larger number of photoelectrons which are emitted. So the electrons emitted from the surface are what I am terming photoelectrons. Now, if you increase the intensity, just the number of photoelectrons emitted, and so the photocurrent increases. But that has nothing to do with the actual energy of the photons itself. So if I wanted to look at a typical graph of current versus voltage, right? Here would be my stopping potential. It's negative because it is the reverse of the potential difference across the electrodes. And this will represent a photocurrent 1. Now, if I have a greater intensity, I would just have a larger photocurrent. But in terms of the energy value, it is irrelevant. Okay? Now, let's say I have a shorter wavelength, then my graph would be here. Right? So here, I have a shorter lambda.